today. And this is the reason why we want to have a cap truss over there. So without cap, your diffraction mode is all the way fractional type here. It's like first mode of dynamic mode. And if you have a cap truss over there, your mode goes in showing fractional mode, and there's a contrafractional point right there, 변곡점. You have a contrafractional point here, right there, and then you change your curvature this way, resulting in the reduction of your diffractions right there. Isn't beautiful, right? So bring small cap structure, try to make your building deformed into curvature, and this curvature with this curvature with your contrafractional point right there. So seriously consider having a cap structure on the top of your buildings when you have a outriggers. Do you follow me? Okay. Okay, this will be a typical drawings for high-rise buildings that is equipped with the with outriggers here and belt truss as well. This outrigger is not seen from the outside of the buildings because of the facade right there. And you see the belt truss. You can kind of guess that you may have outrigger in this particular floor, and you have belt truss spanning for 4 floors. A huge belt truss and outrigger. Right? Maybe you have outrigger with 1 floor, whereas your belt truss going stored that's spanning for 3 floors. It doesn't matter, right? It does not mean that your outrigger is occupying 3 stories, but you have all the possibilities. Outrigger with 3 floors, 1 floors. But one thing you know that the truss is spanning 3 floors right there. And you have another truss for top called cap truss. And inside you have a shear wall. If you want to use concrete, you can have steel braced truss if you want to use a steel frames. And this is very typical construction drawings that you will see for high-rise building, which is equipped with outriggers, belt truss, cap truss. See, now this is very nice illustration that shows outrigger truss, outrigger frames. So same thing here. Very careful. Listen very careful. You can use a outrigger walls. If you want to use reinforced concrete structure, you can go to walls that connects your exterior columns and core walls. Okay, what's the outrigger? It's nothing more than a connection. Nothing more than a connection to increase your moment arm of outrigger jjigae. Don't forget that. It's a very simple concept. If you want to use RC, then you still can use a outrigger walls. But if you want to use steel structure for some reasons, then you may use a outrigger truss. Okay, so you have a freedom to do whatever you need to do for best production of the building design as engineers. And this is all entirely engineering decisions. And if you're a boss, then you have to make the decisions so that people can follow your order and directions. Okay. Until then, you have to follow somebody's directions and learn from the experience and from discourse. Okay. So our leader, whether it is truss or walls, is connected directly to core. This is the role of outriggers. Okay. And again, inside here is gonna be either shear wall if you want to use RC, and this is a brace. The frame is called truss, isn't it? If you want to use a steel, okay. And you learned how to design truss in statics course in fractionals. Well, and you can use that knowledge still in this high-rise building design. And this is column. Okay. So now you got a big picture of what Outrigger can do for you and what you can do with Outriggers and when you need Outriggers and when you don't need Outriggers. The Outrigger is a one ingredient. The ingredient, something like you need when you make a food. Okay? See, Outrigger is one very powerful ingredient, structural components. When you go up until maybe very high rise buildings, maybe over 70, 100. So the Lotte Tower has a couple of outriggers. As far as I understand, Lotte Tower has 2 outriggers. And why don't you go and take a look at some online site to find out the in outriggers in Lotte Tower. Okay, this is not homework. This is not homework, but you want to take a look at the outrigger application in real buildings. So I recommend you to take a look at, okay, 3 outriggers. 3 outriggers. Any outriggers in real building and study that and summarize it. Okay. And that'll really make your project easier and faster. But this is not homework. This is not homework. You don't have to show me. But you have to keep yourself for your future references for sure. Okay, this is my example for you. Okay. Look at that. This is a concrete core, and this engineer wants to use a concrete core. And he has a also exterior columns, and I explained how we cooperate the size of columns into calculation of moment of inertia. And this is pretty simple, isn't it? The outrigger is nothing more than a what? I said wall, concrete wall, if you want to use concrete, or truss, if you want to use steel sections. Right? This is truss. So that the truss is pin connections, as you know, right? Here, pin, pin, and pin, pin. So all the connection associated with outrigger truss is pin. Whereas you may have some rigid connections when you have a outrigger walls here. Okay, that's natural connections for concrete structures frames. But if you can have a truss structure, you may have a pin connections. That's okay, as long as you can just lengthening. You can be lengthening your moment arm, which then increases your overturning moments. And again, this is a outrigger, another application of outrigger from your outrigger cranes, right? And you want to lift heavy loads to very high floor, okay? And this is another schematic view of the outrigger systems, and where you have a windward face and a leeward face where you receive tension and compressions. This is very interesting. Right? This is all you need to know for carrying out your projects. And this is four walls, and you have a outrigger truss attached between concrete wall and external columns here. And you go outrigger this way, right? And then you have a belt truss here, right? So this is a typical drawings illustrations. Then your Outrigger system, if you want to use a truss, then your drawings should look like something similar to this one. Okay, and also I'll show you one of the computer generated Outrigger details before I ending this clip, but this is very useful drawings for your project as well. Okay, what happens here is the Outrigger damping system. Outrigger damping system, and when building diffracts, this Outrigger is gonna go in and go up and go down to try to participate resisting lateral forces, right? And here this part of the detail is very important because the diffractions and how diffraction reduces depending on these details and here. And we talked about damping of the building in previous lecture, and damping of the building is very small, usually like 1%, 1.5%, and we need to increase using a artificial dampers, and I explained. And here, this is good place where you want to put your artificial damper right there. So you want to have some steel plates or artificial damping devices right there, so that when your outrigger touches your damping devices, top and bottom, something like this is that contacting top, contacting bottom, when you change your loading directions and whatever, so that your damping is going to be generated. I mean by generate is that your energy is going to be dissipated or absorbed through this device, so that the energies are distracted instead of contributing to deform your buildings. Do you understand what I'm saying? So, as I said, you may increase your damping in the system like 5%, 6%, but you have to provide the proper damping devices, what you need to provide a artificial additional damping to your system. And without doing that, your building will experience severe deformations because the building damping is very small, not 5 to 6%. Natural damping is less than 2%. I should say 1%, 1.5%, I should say. Do you understand? Okay, this is very important. And this paper was published by these four people. The instructor appreciates the paper published by these four people. They are at Daewoo Construction Company here. Thank you very much. You can see close look at here, and this is your outriggers and your shim plates, and this shim plates will dissipate, absorb energy, distracting the loading from deforming your building. Okay. This is another damping device with a kind of tube in which the liquid is filled. So this liquid try to provide a damping effect on this outrigger movement. When you go up, the liquid try to stop them dissipating energy. When you go down, similarly, right? And this is a damping device is with the liquid. But the other one was a plate. So plate also can provide and absorb energy, and so does this damping device. Okay, if you see the YouTube upload last year by your sunbather, that you will see a little experimental illustrations how the damping devices can be installed in high-rise buildings, and your students, your sunbather, did pretty interesting simulations using a small prototype frames with a syringes, 주사기 syringes, and you want to take a look at it, and you're gonna do probably if you want, okay, but it's not a really big problem, which is very good idea. This is a kind of schematic view of your damping devices there. We have a liquid over there, so that it'll try to retard your deformations. Retard means delay your deformations, so your deformations significantly reduce. This was used in this structure where you have a two outriggers, right? So these outriggers are not, small thing to do. It's big things. It's real things with very fantastic idea, with good economy, and this is what engineers all over the world used to use and love to use until so far, and they're gonna use this in future as well. So you want to take a look at it and make them familiar with you. This is one of my paper that I published some time ago, and here I investigated the contribution of outriggers, and this is for RC, and this is for steel structure, and this is truss, and this is a cold walls. Okay? And here, take a look at same, but everything has been explained already. So this just repeating information that I gave you in this video. And here the outriggers, look at it, outrigger do not have outrigger in this directions, right? You have only outrigger in this short direction, because the engineers think that the outrigger is needed with vibration of these directions. But these directions, the frame itself enough, because you have a long length of the buildings right there, which can provide enough stiffness to resist your diffraction this way. So you don't have outrigger in this directions, but you have outrigger in these directions. If you need, you may have outrigger in both directions. Both directions, it doesn't matter. It depends on your stiffness of the building that you have, right? Okay, it doesn't matter. You have a truss, but we don't have a cap truss over there. So this was from your sunbather projects some years ago, and they have a outriggers in two locations, and here and here. If you stop by the buildings in Seoul, in big cities, you can see immediately where your outrigger is located, because outrigger is always and sometimes accompanied with belt truss. So you have a belt truss in some floors in the building, then you can think of that you have outrigger in that particular floors. Okay, something like this. So you may be able to tell that you have a outriggers right there because you have a belt truss. Okay. Okay, this group has done excellent jobs. See here, they have tried 16 types of designs. They want to find out the best designs based on 16 preliminary designs, and this is what they do in real building design business as well. And this is called a preliminary design stages, and they do perform the 16th combinations of the outriggers and belt truss, and they summarized it here. If you see here, pin outrigger. So I told you outrigger can be pinned when you have a truss members, right? Okay. When you have a fixed outrigger, then they must have had a concrete structures right there. So here, just take a look at one case here. One pin outrigger. Oh, I'm sorry. This is a outrigger, two outriggers, and belt truss, right? Okay, and two outriggers and one outriggers, and and this is no outriggers installed in case 4. Okay, this is how you read this. X, 1 or 2, okay, and belt truss. There's no belt truss here, and one belt truss, a two belt truss. So you can make a combination that you want to check for finding the optimal designs for your buildings. Okay? And here the diffractions are also written over there. Here they have a diffractions is very small, right? If this criteria is based on H over 600, so all the designs are satisfied because their diffractions are smaller than H over 600s. Okay, some of them is too small, like this. In that case, you want to release your structure a little bit more so that you can allow a little more deformation, displacement. So this is too small. If you think this is too small, understand? Do you follow me? So it's up to you. You can end up design with this deformations, or you can release. You can soften your structure a little bit to have a H over 600, vicinity of H over 600. So this is beautiful, isn't it? And they have used a concrete 50 megapascal and 40 megapascal and various location of columns. And they have used a high concrete strength for low-rise part of the buildings, whereas they have a little less concrete strength probably for higher part of the buildings, I guess. Okay. And this is good legend. So, with the outrigger indication, outrigger with the number of outriggers, number of air truss there. Okay, let's take a look at the Midas output here. This is a Midas output. You should be able to have a Midas output similar to this one, and we can understand a couple of things from this Midas output. For example, we have a core wall here. This is concrete, right? Core wall is concrete, and we have a outrigger. How do you know that we have outrigger here? This is outrigger truss, right? Connecting core walls to the exterior columns. And here we have one bay, and here we have two bays. And they have a concrete core walls, whereas they have a truss outrigger frames. Right? So if you have a truss, it's easy for people to pass through this compartment, right? Usually people do not live on outrigger floors. Usually people do not reside on outrigger floors, but people have to go there to check, to maintain the structures. So people need some space to go through this compartment. And if you have a outrigger truss, it's very convenient for people to come across this. Okay, if you have a concrete walls, then you need a big door for people to go through, right? And there's no outrigger in this direction, right? Or just they printed structure in this direction. Because I think there's no walls, also core walls, it's not indicated with this directions, right? So this is what I guess. But you may need a both direction of outriggers if you need, okay? And this is view on belt truss. You have a nice belt truss out there. So when you see the building from outside, you see this belt truss clearly and makes you guess that this is probably outrigger floors. Right there. This is how you look belt truss from Midas output. Okay. And of course, all these connections can be pinned connections for truss member that you want to use. So clear? Everything is very clear. All right. So this is a hand calculations, and they have a overturning moment, x direction and y directions. And as I recommended, they have a strips elements here and calculated the centroid of each element one by one and make a numerical model to calculate the diffraction at the top of the building. So how can you calculate the diffraction at the top of the building or tip at the cantilever? Just nothing more than the area times the centroid for all segment and add them up and give you the diffraction at the top of the building, right? Okay, and this is what they do, right? So they use a just a little formula that you can find any books. So and this is a centroid or length, and this is area, right? And you can divide this strip as many strip as possible to make the error minimized. Okay, and this is what you do. And you can do this using Excels and very easy. You don't have to go to computer, and you can do it by yourself, and then compare with the computer and then yourself and how accurate you are when you use a simple moment area method. And this is the results. That's surprising, isn't it? This is 3D computer modeling, which means Midas. Midas also calculate your diffractions in x and y axis, and they end up with a little less diffractions because they released some constraints and they reduce some design sizes, so they end up with h over 537 with the x-axis and h over 653 with y-axis, and that's very good. It's very good. Good design. And the manual calculation yields a very similar deformations right there. The errors between, not errors, but the differences between these two entirely separate evaluations, which is only 4.3%, and here 9.7%. This is amazing, isn't it? So this is the way you calculate your diffractions before you're going into the computers. Why you need to do with manually? Because you want to decide your starting beam size for Midas input. If you put the beam sizes, which is bigger and smaller into the Midas, then you have to rerun Midas. You have to iterate Midas. You have to go, I don't know how many Midas run you need to come up with the best appropriate design sizes to satisfy the seismic motions, to to get a satisfied designs. So that is very time consuming processes, but you can save that time by taking a look at your diffractions based on the the manual calculations as you see over there. It's beautiful listening. So this PPT has all the informations that they need to carry out the design, and this is excellent way. I don't think any other great engineers can do better job than these students did in school. I'm very proud of this PPT and designs, and I hope you can provide the projects for this particular semester. Okay, is that all right? Any questions? I'm gonna close this lecture on the Outrigger formulas and structural designs. And if you have any questions, you can ask me. And you're gonna probably have some questions, put them on the post or when we meet in class. Then you can ask me a question. This is very important. And next lecture, we will go to tubular structure. Tubular structures, something like this. You make a tube. This is tube. So the subway in England is called London is called a tube, right? Tube is a rectangular shapes. Rectangular shapes are used to provide a stiffness for buildings, and tubular structures, of course, is a very efficient structural system for designing buildings over 100, 150 stories. And they're having a very closely spaced columns with very small windows because they are providing a stiffness for buildings to resist the lateral load. So this is what you see as a tubular structure. And we're going to study how tubular structure can be designed and how they can be effectively designed for your high-rise buildings, which is probably over 150 stories. Okay, so that'll be another quite long lecture next video. Until then, I need you to review the video clips on Outriggers and try to be ready to receive another information for tubular structures. Thank you very much for a long time.